Hello guys, this is the solution of one Otto cycle, step by step. This is 934 of the 7th edition of our book. The image is not very clear, so I'm going to read it. We have a 6-cylinder, 4-stroke spark ignition engine operating on ideal Otto cycle. It takes air at 95 kilopascal and 70 degrees Celsius, and the maximum temperature that the cycle is limited to 170 degrees Celsius. Each cylinder has a bore of 8.9 centimeters, and each piston has a stroke of 9.9 centimeters. The minimum enclosed volume is 14% of the maximum enclosed volume. So the question is, how much power will this engine produce when operated at 2500 RPM? We need to use constant specific heats. We need to use constant specific heats at constant and room temperature. So this is important. Constant specific heats at room temperature. So let's start by writing the main parameters. We change the color of the pen. So we have that the number of cylinders are 6. The bore, which is the diameter, is 8.9 centimeters, and the stroke is 9.9 centimeters. V min is 0.14 of V max. So we can recognize here that since R is V max over V min, this will be 1 over 0.14 equal 7.14. So compression ratio is not given clear directly, but we can derive it from the information that we have. It also said that we can the speed. Sorry for the barking. I'm recording at home. And pressure 1 is 95 kilopascal, and temperature 1 is 70 degrees. We know that the maximum temperature that we can achieve is T3, so we're going to say T3 is 870 degrees Celsius. We also know that we can get we also know we need to use constant specific heats, so that is at 25 degrees, and this can be consulted at table A2. Cp is equal to 1.005 kilojoules per kilogram Kelvin. Cv is 0.718 kilojoules per kilogram Kelvin. This ratio will give you 1.4, and it's a dimensional. And recall, R for air is 0.287 kilojoules per kilogram Kelvin. So before we forgot, remember that we need to change everything to Kelvin. So this is 290. And this is 1143 Kelvin. Okay, so we are ready to start. And we start by drawing our TS diagram. and our PV diagram. A lot of questions that if this is required, it's usually a good practice to have it. So we can start by drawing our TS and PV diagram. People have asked if it's required. Well, sometimes we will have it, and it's always a good help. So this will be our PV. Remember that we start at 95 kilopascal. This is our Vmax, and it will go up until Vmin. This is 1 and 2, and we're going to have a constant volume heat addition, and then we have our expansion. These are vertical lines. So this is our PV diagram. Our TS diagram looks a little bit different. Recall that the compression that we have from 1 to 2 is isentropic. So we have a vertical line. They have a constant volume, then isentropic expansion again. And so it's not to scale, it's just to represent what we want. Okay, so since this is the first video, we're going to do it step by step. We are asked to get the maximum, the work, the net power at 2500. So we can start by just writing the expression that we write. So this is the net power, and will be the net work, the net specific work that we have per cylinder times the number of cylinders times the speed. Since this speed is in kilojoule and RPMs, we need to convert it to 1/second. So that will be divided by 60 for the seconds, and 2 because we have 2 revolutions per cycle. This network should be with all the mass included there. So this is, so we have the mass that we have in each cylinder. So let's see our units. This is kilojoules per kilogram per cycle and per cylinder. This is the number of cylinders, so they cancel. These are RPMs, so this is revolutions per minute. 1/60 is minute over second, so this cancels. And the 2 is 2 revolutions per cycle, so the cycle cancels and the revolution cancels as well. And then the mass is kilograms, which also cancels. So we have kilojoules per second, which are consistent with kilowatts. Okay? So we need to find out W net. We know that W net, the network, is workout, which we have from 3 to 4. Sorry, we have a mistake here. Just as in class, I can get some mistakes, so if you find any, let me know and I fix it. Minus work in, which is the compression stroke 1 to 2. Okay, so let's how do we get workout and work in? It's applying first law to this process. So for first law we have, for closed systems we have work in minus work out plus Q in minus Q out, and will be U final, U2 minus U1. Now, this stage, we don't, it's asymptotic, so we don't have any heat transfer. And what we are doing is work in. So work in will be U2 minus U1, and this will be equal CV, since it's a closed system, CV T2 minus T1. Sorry, it's not because it's a closed system, it's because we are talking about internal energy. So how do we get work out? Well, applying the same, we will have work in, and mark this as 1 to 2. 3 to 4. So work in minus work out plus Q in minus Q out equals U final, which will be U4 minus U3. Again, isentropic, which means no heat adiabatic and reversal. So adiabatic means no heat transfer. And this time we're getting work out of the system, so we cancel this. Solving for workout, we have T3 minus T4. Notice a change because we have minus, so we are multiplying everything by minus 1. Okay. Since this is a constant specific heat, we can get both of these temperatures because we already have temperature 1 and we have temperature 3. The other two can be found with isentropic relations. Okay, so how to get them? T2 over T1. Recall that we have this relation of V1 over V2 to K minus 1, and we can solve for T2. We don't have the volumes, but we do have the compression ratio, which is the ratio of these volumes. Similarly, if we do it with T4 over T3, and solving for T4, again we don't have this relation, but we can erase this and use the compression ratio that we know. So this compression ratio will be 1 over 4, 1 over R, because now before sorry, this also has a mistake. Hold on. This should be B3 over B4. So this is 1 over R. Okay, so we can get this. Let's have it right now. So T2 will be T1, which we know is 290, times 7.1429, 1.4 minus 1. So this is 636.7 Kelvin. Similarly, for T4, we have 1143 times 1 over 7.1429, or 0.14, which is what we got from the text. And the final result is 520.6 Kelvin. So we know how to get work in and work out. Let's get it now. So work in is CV, which is point. Let me fix this so it's easy for you to read. So 7.718 times 636.7 minus 290 is 248.93 kilojoules per kilogram. Recall that this is kilojoules per kilogram Kelvin, this is Kelvin, so we have kilojoules per kilogram. Workout will be the same. Constant specific heat times 1143 minus 520.6, and we got 446.89. So if we have minus and we do the same math, we will have our network to be 197.96. Now, the problem doesn't ask for the efficiency, but we're going to get it anyway. So the efficiency so we have work net, and what do we need to find now is mass, because the number of cylinders we have it. So mass can be found by There's no relation. V1 divided by V1. This is the total volume, and this is the specific volume. Total volume can be found by P, the bore square over 4. This is the area, and times the stroke, which is the length that the piston travels. Now V1 can be found using ideal gas. So we know that PV equals RT, and we know P and T for state 1, so solving for P1. Putting some numbers here, we know that V1 will be equal to 0.287. This is kilojoules per kilogram Kelvin times T1, which is 290 Kelvin, and P1, which is 95, and we're gonna write it like kilonewton per square meter. So we know kilojoule is kilonewton per meter, so that will cancel the kilojoule, the kilonewton, and leave us with 1 meter. Kelvin will cancel, so at the end we're going to have 0.8822 kilojoules per kilogram. Sorry again, guys, it's cubic meter. Cubic meter, 0.88 cubic meter. Now V1, we're going to have everything in international system, so it's P over 4 times the bore, which is 0.089 square times the stroke, which is 0.099 meters. So this leads to 0.0006 cubic meters. Substituting here, we'll have 0.0006 cubic meters divided by 0.8822 cubic meters per kilogram. Cancel, and the mass will be 6.98 times 10 to the minus 4 kilograms. This mass is per cylinder. Okay, so we are ready to compute our network, net power. So net power will be the net specific work, which was 197.96 kilojoules per kilogram times, and this is per cylinder, so I have to add the mass, each cylinder 6.98 10 to the minus 4 kilograms times the number of cylinders, which is 6 cylinders, times the speed, 1/60, 1/2, and this number will be 17.27 kilowatts. So net power is kilowatts. The problem doesn't ask for the efficiency, but we have everything to compute it. We know that efficiency is net work divided by Q in. It doesn't matter if it's the total power, the power of the specific work, because both of them have the same constant, which is the mass and the speed here. So Q in, if we do the first law analysis, we will find out that it is U3 minus U2. I will ask you to do it on your own and find that this is true. If you have questions, you can ask me at class, and this will be 0.718. Remember, this is kilojoules per kilogram Kelvin, times T3, which is 1143, minus T2, 636.7. So this is 363.5. So our efficiency will be the network 197.96 divided by 363.5, which gives us 0.4446. 0.5446. So the efficiency of the cycle is 54.46%. Okay guys, thank you. So watch the next video where we are going to have another Otto cycle. It will be a little bit faster, and then we're going to construct an ITESM program. Thank you. Bye.